Hi everyone, welcome to the last of the series of the Science of Science. And as you know, today we'll be having a panel discussion. I hope that you will be very keen to join us in some questions and some comments. I know we have quite a few scientists in the audience who we would love to hear opinions from this side as well. So just to let you know how we're going to run this, I received a couple of questions via email to the email address we put up. And so I'll start with those. And then, if there's any comments on those questions or other questions, we'll move on to those. Okay, so I'll keep an eye out for comments. So I've just typed out the couple I've got here. The first question we had was, in psychology, an observation is often an account of something. By definition, this is subject to a personal bias. For example, the phrase is used, I see things as I am, not as they are. How does this relate to empirical evidence in science? So I thought we could start, Johnny could start us off on that.
Question. And I think that this is, in my talk, I said about the fact that expert opinion had been downgraded in the evidence ranking. And I think it's in line with that comment. And I think that we've even though we start, everyone starts with an observation from your own, certainly in medicine, clinical observation of patients or groups of patients. But there is, in the current sort of scientific method, moving towards trying to take that element out. And once you have your observation and your hypothesis, then going about rigorously trying to test that. And I think that's where the empiric evidence aspect comes in. I think that the first part of the question raises psychology, and that actually, if you look at it, that's an area where we've really struggled to deal with that, because it's got the psychology of the observer, the doctor, the patient as well. And I think it's probably evidenced by the fact that they keep rewriting the DSM-4, which is a psychiatry manual, because there everything's described based on clinical syndromes. And if you've been, there's a lot of press about that at the moment in terms of the whole DSM-4, which is the Diagnostic Statistical Manual, which is basically a group of classifications of psychiatric disorders, where they're now they've rewritten it, I think it's in its 5th edition now. But there are a lot of people within the field saying that actually the only way we're going to get to an empirical description is to move to the molecular. So when we start to understand the molecular basis of psychiatric and psychological disease, we're then going to be able to flip the whole thing on its head, essentially, and move away from what are really exactly that, observed opinions, to a place of more objective, empirical classifications and groupings of disease. So okay. I think that's what I'll start with as a comment.
And Ian, you had some ideas on whether you could actually be objective in gathering evidence, right?
Well, I went back after my talk yesterday. You always finish a talk thinking, did I say something wrong? And so I went back last night and I went down the rabbit hole again with Mr. Cook and everything around the 97%. And what I find really interesting is that I said some rather unkind things about people who I don't like yesterday, which is the nature of bias and confirmation bias in particular, when you read a set of statistics and you want them to say the thing that you want them to say. I think the key thing about it with regards to empirical evidence specifically, which is not statistics, and I think statistics are a whole different realm of data gathering, data sets, data interpretation. If we look at the basic idea about empirical evidence, there is this issue, certainly in the social sciences and in fields of study like anthropology, which often questions the veracity of the empirical evidence based on the person who is gathering that evidence. And I think that's always going to be an issue. So it doesn't necessarily say that empirical evidence has no place in the scientific method, because obviously it does. But it does mean that when one encounters a scientific study from a field outside of it, and one of the things I found, by the way, when you look at things like climate science, is the amount of, I don't know what the correct phrase is, but people swinging their degrees around, basically. You don't know this because you don't have a physics degree, or you can't comment on X because you don't know anything about stats, or you have no right to saying this because all you've done is X and not Y. there's a very, and it's a field that is notoriously broad. People who claim to be climate scientists might have degrees in everything from oceanography to geology to engineering to a whole lot of other fields, all have specializations that allow them to comment on it. So it's a very difficult field. So what becomes empirical in that environment, and this leads to something, it's to the idea of modeling. I don't know if anyone talked about modeling in their talks, but one of the key kind of conflicts, if you want to call it that, between sort of sciences and social sciences is this notion of modeling and the value and the ability of modeling to be used as a sort of tool to test theories and to put theories out into the public sphere. So I think it's not so much about the empirical evidence within the idea of scientific study. It's more about what happens when that evidence encounters a field of study that has different research principles and different aims for those principles. And I think that's where, and as Johnny said, in medicine, that's a very good case. We have psychology engaging with medical science. And then you're going to get there are conflicts, but I don't necessarily mean conflicts in an antagonistic way. They're conflicts in as much as they require an understanding of how those two fields are going to engage with one another.
Thanks, Ian. Are there any comments from the public? Not as yet, but this leads quite nicely into another question. I think I want to skip to number 3 here, which was when science is defending against pseudoscience, a strong emphasis is placed on the ability to replicate results under strict test conditions. And this is kind of what you would think of as an observation in science. If you observe it again, you get, the same thing. So the first sub-question here is evolution exempt from this requirement? Nusha, can you comment on that?
Yes, I did see the question and I thought, but why would evolution be exempt from this? Because evolution is really based on scientific observation. There's been a hypothesis, it's been tested so rigorously. So I would say that evolution is not exempt from this. And people might say, but can you replicate the evidence? And to a large extent we can. I mean, if we think about the fossil record and how the fossil record supports evolution, we know that, for example, if we look at transitional animals, we might find one transitional animal, and then a few years later, we might find another, and that reinforces that original hypothesis. So in a way, evolution is a scientific discipline. It is well embedded within science. The whole process of understanding evolution is scientific. So I feel it's not exempt from this. And I'm not sure if anyone wants to discuss this, but that is my feeling, is that it should not be exempt. It may be, it's a different way in which one actually replicates the results, because it's not immediate. It depends on what you find. But if you have more and more evidence that supports this notion of what evolution is, then I guess you are replicating.
Yeah, it's slightly different in a way because you don't have the option of setting up an experiment to replicate these results.
Or you could also, if you're doing an experiment where you're working with fruit flies, for example, and there's been many examples of evolutionary studies looking at populations of fruit flies, and because they are a population you can work with and you can treat with differently, you can replicate those results. So it really depends on what one is testing and how one is testing. But in many cases where it can be repetitively tested and replicated, there's been good evidence for that.
Okay. I think Jeff has something to add.
So I was going to say that it's not unique. The application of this question is not unique to evolution. A field like astronomy or cosmology would suffer the same sort of scrutiny, because it's also a field where you can't really replicate your experiment. There is one experiment. It is the universe. I wish we could replicate it. So you have to observe, and I think that the thing that differentiates things like cosmology and evolutionary theory and astronomy from what you would call laboratory science is observation versus setting up the experiment and doing it again, and replication. That said, though, this comes back to what Ian was saying. Modeling plays a very important role in these sciences. So, you have a theory about how the universe evolves. You can set up a model, and you can watch how that model responds to the same conditions that you set up. So, it's experiments, but it's experiments that you do numerically on computers, etc. And I know you can do the same thing in evolution. You can set up a population, have that population respond to a certain forcing from the environment, which is really what evolution is, and see how it evolves. So, and I think this kind of leads to question B: is science itself evolving? And I think that back in the day, where science was the playground of the aristocrats and the monks and the people that had the free time to sit and think all day. That kind of science was entirely different from the science that we do today, which is collaboration on global scales, modeling things using computers, analyzing data. And so, as a response to the second question, I think, yes, science itself is evolving to deal with these kind of questions that reoccur in different ways.
Ian, do you want to comment?
I'm not a scientist. But what's interesting about the idea around the reason why I mentioned modeling is that one of the key debates in climate science is this idea that everything that's been talked about is in the future. In a way, it can't be tested. So, the grand claim against climate science is, well, you said in 1995 that there would be X percentage in temperature change by the year 2015, and it hasn't happened. So you guys are wrong. If all these predictions turn out to be wrong, then how can we trust any of the science that you do? So one of the key problems with there's been numerous talks about the famous hockey stick graph that was developed by Michael Mann. So I think the key thing about it around modeling and around this notion of testing evidence is that one of the biggest problems with climate science is that everything that we have is based on what hasn't happened. So the testing that is happening, and this is the idea of science being evolving, is that each year, so even now, there's a huge claim went up the other day that 2015 was the hottest year on record. 19 of the past 20 years have been the hottest years in human experience. And yet there are websites that claim that 2015 was one of the coolest years in the past 20 years. So how do you get, what is the testing that gets us to that conclusion? And then you have to go down the thing and look at how they get to that point. So I think what's interesting around modeling is the fact that it requires interpretation on the one hand, because it is a model, and you can take the data that's collected to produce that model, and which is what happens with climate science, with climate skeptics, and say, well, I've taken the data and I've produced this model and it's different. And we can only know the value of those models as each year the data sets grow that suggest that model might be changing one way or another. And there might be a moment where there is a kind of radical intervention. There might be one scientist or one group of scientists who finds something, and that radically changes the direction. It might even reverse the direction of that. But as long as we have a model for something, it is only that, a model. And then that reverts back to the point I made yesterday about risk, is that if we have this model that says 50% chance of X or 50% chance of Y, do we act on the chance that the one is wrong? Or do we act on the chance that the one is right? And that's where I think the idea of modeling and replication becomes really, really critical.
I've just got one comment to add to the end as well. I mean, which was question C, which said, at what point might today's panel decide that future science could no longer be recognized as scientific? I think I sort of will answer that in a tangential way by saying that in medical history, if you look back in terms of the discoveries that have changed medical histories, a lot of them have come from outside of medicine and have been technological. And in fact, there was a set of sort of just kind of discussions done around scientists or and this was outside of medicine, but particularly in medicine, getting experts at a time to predict the 10 years from now, what will the science of their field look like, be that whatever discipline they might be. And what they found was, on most times they were wrong. If they just looked at 10, and some journals even ask you to do that now. They say, you write an article and then they say, will you put in what the future of that particular thing will be? And I think, to me, what that speaks to is the fact that we are the forces that will drive the evolution of whatever scientific discipline we are might come from totally out of left field and actually are quite unpredictable, such that within your own scientific field, you kind of start to think of yourself as as an expert in being able to somehow see where that field's going to move, but actually most of the time you're going to be totally wrong. And
That makes it so exciting, right?
yeah, well, yeah, and I think it says that in a way that it's definitely evolving, and we don't even know which direction it's going to evolve in. And to think now we're going to be able to predict how that's going to be, I think is probably incorrect.
Anyone here want to comment on that? Right. Great. Thanks for that. There was another question here.
Yeah, why all the confusion? How many scientific articles are two completely contradictory sessions maybe that have been peer-reviewed and supported by the peers, and they offer different opinions about a particular subject. How reliable is this peer-review process?
Yeah, great question there.
Not at all. I mentioned, a very simple case. I mentioned someone yesterday, Lord Monckton. He's quite a character. He claims to have developed a cure for AIDS and a lot of other things. He really genuinely is a snake oil salesman and a peer, or an alleged peer of the realm. But one of the things that one of the claims Monckton made at one point was that he was a reviewer for the IPCC, which of course lent him credibility when he was speaking in front of the Congress in the United States. But in order to be a reviewer for the IPCC, all that one had to do was to indicate that you were willing to review. It didn't mean that you were actually necessarily being sent documents to review for the IPCC report. So the problem with peer review, and this applies throughout disciplines, even in, is that there is one of the big scandals around the leaked emails in the IPCC was the fact that there was a kind of a coterie of key scientists who were ganging up on people who didn't fit into, they were basically doing end runs around the peer review process by sending certain papers to friends who would agree with it, and then, so the peer review process is always is never infallible, and I think the problem with peer review is that if you are, for example, writing a sort of climate skeptic paper, or if you're writing a sort of a different paper, there will always be someone who in the field who will clearly like what you say and will publish it. And it's been one of the biggest problems in the way that research in general has been driven by these agendas of I don't know what the correct word is, but it's essentially bean counting and a sort of an actuarial approach. So you'll be told that your impact is 3.14. That's your value in your field, based on how many people have downloaded your article, tweeted it, cited it, and so forth. And those things themselves are also, people are constantly fleshing out their essays by citing pals in the industry, so it pumps up their citation ratings, and that's rife throughout the disciplines. So I think there is a real sense of one of the profound problems for research as it relates to people, especially outside the academy reading it, is that if you say, well, this is a great paper because X number of people cited it, well, that doesn't really necessarily mean that the paper itself is of value. A lot of writers will write something that they know is contentious because it will get cited by people who refute it. So this is why I think the idea of citation and peer review is deeply problematic, and it can't be the sole judgment of the value of the research is its peer review, but it certainly explains, in your case, why you will often find completely contradictory. If you really wanted to investigate that, if you found two publications that contradict one another, what you'd really have to do is to look at the history of those two publications, those two journals, and find out whether they in themselves have got any inherent bias towards, I'm certainly in the vaccination field that would be true. If there's a certain journal that's a little bit flaky and says one thing, you'll find that there's a pattern of those papers being produced. And again, that's hard work for you,
But I feel on one hand, do we really want journals to impose like a strict censorship of stuff, or does most of the peer review happen by the peers who actually read it post-publication? So I think there's one question at the back there, after Jeff.
I think it needs to be reported that several Nobel Prizes have been won by several Nobel Prizes.
That makes me feel better.
were searching for something else.
That's right. Jeff.
Can I maybe just go back to the question about peer review? I'm not a big fan of peer review. As a general statement, I'm not a big fan of journals. I think that journals are an archaic construct that in this day and age, when we're dominated by the internet and roughly freedom of information, journals are a bit of a mafia. And, you know, especially in a country like South Africa and, you know, much of Africa, journals really hold universities to hostage. There are many, many examples of where journals will sell to the university one publication, one journal that publishing houses will sell to the university one journal that they want, bundled up with 5 journals that they don't want at an exorbitant price. Today, we have something called the electronic bulletin boards, or the archive, ARXIV. And it was set up by a physicist in my field, and it's now expanded to a number of different fields, including chemistry and computer science and mathematics. And what it is basically a forum that once you write your paper, you upload it onto this thing. And unlike the peer review process where you submit it to a journal, it goes out to at most maybe 2-3 individuals who, you know, have essentially control over whether that paper gets published or not. Here, you put it out for the entire public. So unlike in journals where your audience is really very small until it gets published, but by the time it's published, it's an enormous thing to retract an incorrect publication from a journal. It takes a long time, it takes a lot of red tape. Here, you're putting your entire reputation on stake for anyone who wants to comment on it. And on the archive, I've noticed over the last couple of years that when you do something and it's wrong, people don't write to you an email and say that it's wrong. They write a paper telling you why you were wrong and put it out for everybody to see. So this is the nature of scientific communication changing, right? Because of the nature of the world we live in today. So in addition to, you know, science evolving, the way we communicate science to the public is changing. Sometimes for the better, sometimes for the worse. You know, like things like Twitter, for example, freak me out. It's you know, on Twitter, everybody has an opinion, and all opinions are taken to be equally valid. But you know, part of the point about expertise is that not all opinions are equally valid. Yet, you know, in today's world, that barrier seems to be disappearing more and more. And so things like, you know, anti-vaccination are starting to really make an impact because of this trend.
Yeah. Thank you.
Yeah, I just want to go back also to the peer review, and I agree with Jeff that, you know, the way the fields are moving in all aspects of science is to more this open access and open peer review. In my field, there's a journal called Peer J, which is, again, before you can submit your paper to the journal, and it goes to individual reviewers, but during the time that the paper is being reviewed by a select few people, it's also open to anyone to access. And people can comment on the review. Once the reviewers have reviewed the paper, the actual review is also put onto the system. Because what we find is that the peer review we think is a very honest, open process, but in fact it isn't. Because often there are different camps, there are different views that people hold, there are laboratories with opposing views, and if you try to publish in Nature or Science, and if one of the editorial board members, for example, is on from a different camp, your paper wouldn't even pass the editorial board. So often in these big journals that are very well known, like Science and Nature, it's extremely tricky to get past the editorial board. So you pass the editorial board, and once your paper is then sent to peer review, you then have to hope that it's going to an objective peer review. Because often there are these different people who hold different views and wouldn't want your paper to be published. But now, with open access and these open ways in which people are reviewing, you circumvent these biases. And the other thing, one more thing, just I don't want to monopolize the microphone, but one other thing I want to say is that they are also, because of these biases that exist, we know that many people today, the good journals, are actually asking people to review papers blindly. That is, your paper is sent to someone, but your name or your co-authors' names are also not indicated. So that when people are reviewing a manuscript, they're reviewing it objectively, not because so-and-so said this, and so-and-so is a guru in the field, and he must be right. So I think that's also an important step.
Thanks. Have we got...
Yeah, I've just got one more comment there as well. I think it becomes very difficult, the peer review process too, when you start to get to the fringes of very complex science too. In a few medical genetic fields, that's been an issue with some publications where there are only about one or two other people that understand what you're even saying. So, and then that's where your individual biases of those particular people really come into play. And I think from my own sort of issues that I think this new kind of way we're moving in scientific communication poses is the question of, on the internet or wherever, how do we know if someone's an expert? And I think that's a real challenge for us right now in all fields. And how do we know, and what criteria we use to assess that? So we can then value. And I think what it does, at least for me, is it tends to make me more skeptical about anything. And I think that in so many things, like in medicine, certainly, you may have a very good idea that's a single publication or something, but inherently now you need to be skeptical of that idea until it sort of emerges. And this is one of the things I always say to people about pseudoscience. It's like if somebody was really sitting on the next, plant herbal cure for cancer, then that would cure so many people if it really consistently worked, that would start to emerge just organically in our fast-moving world, such that there would be a mass swell. And so actually, even in early ideas that may well be scientifically proved to be correct, I think that we now live in a time where you need to be, in a way, more skeptical. At least that's my response. I don't know how other feels about that.
One more
So
comment.
Very brief comment at the end. One of the key things about journals as well, which Jeff has picked up on, is there's an inherent Northern Hemisphere bias. There's a huge, and Western, I mean, there's a huge checklist on the internet of like so-called junk journals, and virtually all of them are from the global south. And of course, that list is kept by scholars in northern universities. So it's a key problem to the way knowledge is disseminated. And linked to that is the idea of duration, which we haven't picked up. I mean, we've all been rejected. I think I've been rejected a few times, and I had one application where I was told, you've got to go for this journal. It's the top journal in your field. So I thought, great, I'm going to try and get my big A-listed journal, get my name up in lights. So I sent through this massive, different to the sciences, they write like, 500 words and 20 of them write it. And humanities, I've got to write 12,000 words all by myself. So I subject this monstrous thing that I've been slaving on for months, and I get this very cheerful note back from the editor saying, thank you for your application. The turnaround time for published articles, now these guys publish 6 to 8% of their submissions. Okay, 6 to 8% of their submissions. They said the turnaround time for published submissions is 24 to 28 months. So I'm thinking, so it's not really that current then, is it? I mean, by the time our article's actually gone through review and revisions and you've chosen to publish it, if you do, and as a lot of journals will do as well, they embargo it. So if you submit your paper to that journal, you can't submit it elsewhere. So you wait for the 8 months review to come back before you can even think of submitting it elsewhere, which also makes a mockery of this whole sort of notion of up-to-date science and everything. And that's the reason why, and I completely agree with Jeff, I'm totally over journals in general, and I think the peer review process is so fraudulent and so sort of suspect in so many fields that it actually nowadays is, and I'm involved in it. I mean, I review stuff all the time, but it really is problematic.
Well, I think you certainly hit on a nerve there with all the academics. Right, there's a question in the orange shirt, yes.
much better than from comments.
Yeah, a valid point. There's another gentleman here. Thanks. I think, yeah, we have to find a way, I think, a middle ground between the current and a different process. So.
No.
I think
Hold
not.
on. So let me start by saying maybe mafia was too strong a word. So secondly, I don't disagree with you. I think that peer review had its place. I think that peer review needs to, the idea of peer review needs to be revisited, because I think more and more these days, these issues that we've raised are starting to play a role. It never used to be that way. But for example, and this is just me, I'm sure Anicia gets much more, but I get requests, I get on the order of 15 requests a month of papers to review. If I take 3 papers, each paper is on the order of 20, 30 pages, and it's chock-a-block full of mathematics. There's no way that I'm able to meet those my obligations. So I take maybe 1 a month, if that, and it's still, reviewing 12 papers a year is really taxing. So what happens is, I know colleagues who take like 3, 4 a month, and you really can't do justice to the article. I think we live in an era right now where there are other alternatives, and I don't advocate Google, actually, I really don't. But the archive is becoming more and more such a source for a change in the peer review process. It's not perfect, by no means. One of the things about putting out a large number of papers every day is your signal to noise ratio, goes haywire. So you need a way to correct for that. You need a way to sift out the good signal from largely noise. But we're getting there. And I think part of this is recognizing that peer review is something that used to be good and needs to be changed.
Thank you. I think let's move the discussion away from peer review for a while And we'll go to a question that somebody had more on the scientific method, which was the process by which a hypothesis might become a theory has been covered in this course. What about laws such as Newton's law, Boyle's law, gravity? Does modern science still have laws, and can a theory become a law or vice versa? Jeff, do you have a comment on that?
Yeah, actually, it's quite amusing. I sent this question to my wife, who's a physicist, and we had a heated argument yesterday about what exactly was a law and what exactly was a theory or a hypothesis. And it's interesting because I think we're both largely on the same page, but we're very different with regards to the way we interpret these things. So for me, and let me just tell you my view because I think I'm right. For me, is this being recorded? For me, the use of the word law in that context, Newton's law, Boyle's law, law of gravity, etc., is an archaic usage of the word. I don't believe we use that anymore. I think that each one of those examples up there is something that fits in between an observation of some empirical data and a theory. So hypothesis, the way I used it in my lecture, is something that's in between a wild guess and a theory. And a law, I think, fits in between the observation and the hypothesis. So I don't, I try to think very hard about in physics, anything that we would call a law, L-A-W, in the same sense as you would say Newton's law, Boyle's law, law of thermodynamics. And actually all the laws that I could think of were all sort of tongue-in-cheek usage of the word. Moore's law, not really a law, it's an observation of how computers changed the progress in computing, for example. You can think of one?
No, but that's exactly what I think a law is. A law is just an observation. It's not an explanation.
Correct.
Whereas a theory is an explanation of that observation.
Correct.
So
the way I would say it, let me take Newton's law as an example. So here's Isaac Newton making an empirical observation. You roll some balls down an inclined plane, and you see that there's a relationship between the force and the acceleration. And you see that this is a proportionality relationship, and you recognize that there needs to be some constant of proportionality to make the relationships work. So you have F equals ma. And this becomes known as Newton's second law. But there's no inherent explanation of why that works. It's an observation coded in a relationship, coded in an equation. All of them, Boyle's law, gravity, law of thermodynamics, all of these are relationships between various things that you can empirically observe. Right? You watch how gases work and you make an observation about that. The real explanation, for example, of the law of gravity, Newton observed and made an observation and then had a hypothesis and wrote down a relationship and coded it in F equals g m1 m2 over r squared. But it really took Einstein and in a very real sense the scientists of today to try and understand why gravity behaves in this way. This is something that this is part of my active research program. We still, to today, don't completely understand how gravity works. And so we test these ideas. We have hypotheses, and we test the hypothesis, and you test and test and test, and the hypothesis slowly evolves into a theory once you have lots of correlated evidence to support it. Can a theory become a law? In my opinion, no. I think a law is something that's less than a theory. I think a theory is something that, a law and hypotheses evolve into.
Thanks. Any comments in the front there?
Examples come to mind. We've got That's 3 to 1. One that we hear so frequently about fatality in people. Nobody asked why all cars are designed to exceed speed. It's there, but it's not yet. Certainly,
Thank you. There's a comment there. Thank you. Nisha? Oh, it was how you convey something that as a scientist you would know from technical study, like the fact that cow's milk has immune cells in it, to a general audience.
I'm going to be very brief. I mean, I think Johnny's got an answer to that particular sort of case study. One thing I always remember, my father was a physics teacher for many years, and he did a lot of outreach education. And one of the demonstrations that he did for many years at the Sci-Fest in Grahamstown, which always stayed with me, was he got these kids, like standard 5 kids, to make their own comet. And even in my own thinking, I always conceived of comets as being, because they have a tail, they're sort of bright red and whatever, as being hot. And my dad's thing was clearly these are dirty snowballs. So he's got these kids to make a comet with dry ice, and he used to pour in a bit of Coke and a bit of mud and whatever stuff you could find, stick it together, and then when you do this, holding it on, of course, it leaves a little trail behind it, and there's your comet. And it was a sort of 10-minute demo that completely transformed something that's quite complex and celestial into something that was literally in their hands. They could actually make their own comet and could see how it worked. So I think one of the key things from a media perspective, sort of knows from the other side of the fence in a way, is to get scientists to think about how to communicate in ways such as metaphor. I mean, that's either a demo or a metaphor. And obviously there's a risk of always dumbing down. When you try and do it in that way, there's always a risk you're going to leave something out that's quite crucial. But I think one of the ways in which we think about it is to try and think about how does what you think about, for example, your cow's milk example, how does that relate to the people I'm talking to in their daily lives? How can I take what I know and relate it to what they know? And then you're going to have a successful communication. If you can't, and I think obviously some scientists are more able to do this than others, good teachers can do it, is that how do you take your field of knowledge and imagine it in a different context? And I think for some scientists that's very hard, or they know what it is in their heads, but they can't think about that transformative moment. But I think that's really the key to it.
Thanks. And I think that the question you're raising there is a challenge for us in moving forward, because I think that it's a very interesting thing in the line of what I was also saying about sort of how do we know who's an expert, is the internet is making information so readily available, yet often we're not providing from a very foundational level the tools for people to even have basic access. And I think we have to come up with inventive strategies. So Ian's suggesting metaphors. I think that's one option. The other thing that's recently sort of now growing at a university level is small online training courses. So little sort of, everybody wants to watch YouTube. So little 2-minute YouTube clips on simple concepts of immunology. And that could be targeted at the very young, school kids, basically. And that's part of, I think it now definitely moves into education, because the education of the future, we have to decide what are essential now in modern sort of society to know, basically, and teach our children. And I even read an article where somebody was saying that memory as we know it will also change. I mean, and the impact of this you can even see for yourself, because, when I was growing up, I used to have to remember all the telephone numbers of like my home and my mom and dad. Now sometimes I struggle to remember my wife's number. Why? Because I put it in my cell phone and I don't think about it and I dial that. So somebody, this article I was reading was saying that what we'll have to know in the future is not necessarily a list of facts we have to remember, but how we access that information on whatever device we have. That's what we have to remember, and how those things work. So I think this is an area which is evolving, and I think it's a challenge, because the flip side of it is a while ago I was having a discussion with some friends of mine whose dad was a motor mechanic. And I was sort of saying to him how I met this person who didn't know that the heart pumped blood around the body. I met somebody who was like, couldn't know about it. And I was horrified about this. But then he said to me, well, do you know exactly how the engine in your car works? Do you know about pistons and carburetors and how they all connect together? And I was like, well, sort of. And I was a little bit rusty, but his point was valid, right? So and that becomes an educational level, which is like, what level do we need to take the lay person in society to be able to understand across disciplines or across the scientific method, and then where does the role of sort of experts, where we will actually say, well, we don't need every person to know about this in detail, and we need to rely on experts to say, you know what, you can drink milk, or you can't drink milk, and we must believe that in some way,
Thank you. Was there a question from the side?
Sorry, can I just say something
yes,
on the same
Anusha.
point? Yeah, I think this question about communicating science to the wider public is really very important, simply for this reason that people need to make informed decisions about what is good for them and what isn't good for them. But the big problem that we face here, and particularly in South Africa, is that we largely have a public that doesn't engage with science. I mean, the fact that this room should have been packed, because we really need to understand, all of us make decisions that affect our health, that affect our lifestyles, that affect who we are and how we live. And most of what we do relies on science. But people make decisions because exactly what Ian spoke about in his lecture, there's so many influences that allow people to make decisions. So one of my pet hobbies, I should say, is to get scientists to communicate their science more effectively, because I really feel that we don't want everyone to be an expert, but we really feel that if people can make the right choices, if they know how to make the right choices, how to investigate, the way Ian told us, to investigate the different arguments, to be able to assess what is good for you and what isn't. But not just to say, because somebody with the title behind his name said this is good for me, I can do it. That's not good enough. We have to be able to have a really good crap detector. You have to know what's good and what isn't.
That's right. And of course, I mean, the public money funds most of us anyway, right? So, one quick comment here.
Still valid.
Yeah.
Sorry, I didn't
think
say
we were
that. I didn't say
saying-
that the laws were not true.
Technology is different. In technology, there's not one factor which makes and vaccine.
Can we? Oh boy. Quickly.
Okay, sorry. I was talking about the difficulty of predicting from animal models what will happen in humans. And the ethics committees tell you you cannot touch a human if you have not shown that it is not toxic in animals. That is perfectly true, but at some stage you have to go to humans. Okay? You can try all the animals you want, everything is okay, and then you go to humans. It's happened 2 weeks ago. It was mentioned earlier this week. A catastrophe, a terrible thing happened because 2 people who were candidates, the first people, the first people who got that you have to give it to a human, otherwise you'll never know whether humans can take it. And you can do as many animals as you want. You have to do it to humans, and that's why you have candidates who are willing to take a drug. It's been shown that it is not toxic. But sometimes mistakes happen, or the unpredictable happens, and the drug that was perfectly fine in lots of animals is not fine and kills people. Thanks God there are candidates who are willing to try that. The chance that this will not be fine is quite visible, but phase 1 trials are absolutely necessary. Otherwise, we will never get any new drug at all.
Okay, thank you very much, sir. Any comments from the front? Oh, you can't hear. Okay, can we move on to one of the questions that we got from the audience? So there was one short question, actually. Creationism as an explanation of life on Earth is clearly scientific nonsense. Could one describe creationism as evolution denialism in a way?
Well, well, now I know why it was sent anonymously.
No, it was.
But look, let's dissect this a little bit, okay? So we all know creationism, and in my talk I told you all the different creation myths there are in the world. And let's look at what denialism is. And I think if we think about denialism as a person who doesn't, or people who don't accept the evidence or well-supported evidence, we would call them a denialist. And I think I've shown you, I hope, in my talk, that evolution is incredibly well supported by a whole body of testing, by a whole body of knowledge. So it's a well supported theory in the full sense of the word theory in the scientific sense, and it is therefore well supported. And people who don't actually understand or accept that evolution is real, I think it's quite fine to call them an evolutionist, a creationist and evolutionist denialist.
Okay.
That is my opinion.
Thanks.
I don't know.
Just quickly, I think the key thing about denialism, because climate change denialism is another kind of denialism that's come up, slightly different again because the science is murkier. But I think denialism, one of the problems with that particular sort of tagging is that it implies 2 things. A, it implies the fact that one position is completely incontrovertible, which maybe in evolution is easier than it is in climate science. So if you're a denialist, but there's plenty of sites that talk about how people who believe in climate or global warming are called warmists, which is, so if you're a warmist, you're a denier of the other side. But I think the more important thing is that it's possible to have a view that chooses not to follow evolution, but doesn't necessarily make you a creationist, and it doesn't make you a denier of evolution. So I think one has to be careful of saying, well, this community over here have got a particular worldview which has been, which is thousands of years old, which is perhaps conservative and unchanging. It doesn't necessarily make them denialists, because that's basically judging that community by our own sort of standards of scientific discourse and everything else. So I think we have to be careful sometimes, and the internet's a great place to throw around these tags. But I think often because it's not face to face and it's basically shouting into the ether, what you often get left with is that you don't actually know the context of the person you're debating with. You assume that that they come from the same context as you in terms of education and background and everything else, but they might not. So I think sometimes the denialism tag it deafens the conversation, and so I mean, while I think in this particular instance there might be a cause for it, as someone who sort of studies languages, I also think, well, it's a meaningless. You wouldn't need to use the denialism tag, because what is your purpose in actually stating that to begin with? I think that that to me is more important than whether it's denialism or not.
Thanks. There's another question from the audience, which is about ethics in medical research, actually. So the question is why does first do no harm not apply to non-human animal tests when animals can feel pain? Such experiments are not carried out on severely mentally disabled humans, so intelligence is not the cutoff point. If the reason is speciesism, then why will it not be ethical for a genetically engineered, super intelligent, post-Homo sapiens species to experiment on humans the way humans now experiment on other animals? That's a mouthful, Johnny.
No, I really like this question, though, because it was sort of like a great extension from a sort of a standpoint that the person writing the question clearly has, and then a sort of extension into a kind of thought experiment. And to me, it prompted me thinking about what Peter Parker's dad says to him, Spider-Man, says, with great power comes great responsibility. And to me, that sort of sums up how I see animal research. And I think that it's not actually true to say that the ethics around animal research and the way we treat animals does not take into account that they experience pain. I think that, in fact, at the moment on the UCT Animal Ethics Committee, the chairman is very strongly anti-animal research, which makes the process and the rigor behind getting ethical approval to conduct research in animals exceptionally rigorous. And so I think that probably on the strength and backing of the lobbying behind animal rights activism, I think has come a review of that process and a need to take extra precautions and extra responsibilities. And similarly, I think that that would probably be true for what happened if we had a super advanced human operating in some that clearly had kind of, because one of the things is with animals is that we can capture animals, we can exercise our power over them. And I think that that's really what's referred to in the later part of the question. There's some kind of weaker species of any kind, and it's extended through to weaker humans. We have some power and responsibility over them. And it's actually the same in terms of the way as society we decide to treat people with mental handicap and those things. It's like we have a great responsibility for that. And so I think that to me, it's about how we manage that responsibility as a society in any dealings we have with the environment and other species that have less ability to exercise their rights. So that's what I liked about the question. Is it kind of moved through.
And you can watch The Matrix, because that's exactly what happens in The Matrix. We are the batteries of the future machine, and so I mean, I think the other key thing is from a humanities point of view. I mean, a lot of my colleagues in the environmental humanities deal with sort of animal studies quite profoundly, and there's a strong field of study in anthropology and animal studies that is virulently opposed to any form of animal testing on those grounds. So I think, I mean, Johnny's made the point with its particular scientific application, but morally it's not a given, and I think it's increasingly less of a given even in medical sciences, and it's become again one of those areas where if you read people like Donna Haraway and others, for example, the movement between conventionally considered humanities discourses into scientific discourses has become more profound. You get scholars who are operating in a way in both fields, as opposed to the kind of older notion where you had a set of particular scientific kind of silos, and then you had the sort of humanities and social sciences in a different place. I think there's much more of a merging of those fields in particular scholars.
Thank you. Yeah, one comment from Jeff.
So I think, touching on what Ian just said about the sort of dismantling of academic silos and disciplinary silos, one of the things that I see happening a lot is sort of interdisciplinarity becoming more and more of a driving force in the way science is done. Let me give you an example that feeds onto this idea of having to test on animals first. Science is changing, and I think today more and more with more computing power, mathematicians, applied mathematicians, people that do mathematical modeling are getting to play more and more of a role. I'll give you an example from my own undergraduate class, where we try to model the human heart. And you can set up a mathematical model of the human heart that is so precise that the simulations that we can produce on a computer and an ECG would actually take a cardiologist to distinguish between the two. So that is to say, we can simulate the way the human heart works under various conditions so precisely, not my undergraduate class, they have other problems, but scientists, mathematicians, can simulate so precisely the way the human heart works that it would take a cardiologist, somebody trained in understanding what these patterns look like, to tell the difference between a simulated ECG and a real ECG taken from a real heart. So the reason you want to do these kind of things is because you then introduce some medication to prevent heart attacks. You can see at a molecular level how that medication interacts with the chemistry of the heart. You can simulate this. You can run a simulation, and you can see how the heart would react. And you then the only thing is you have to take this seriously. And if you take it seriously, you don't actually have to introduce testing on animals anymore. This is not where we are right now, but this is where we're going. And I think it's important to realize that the upshot here is that science is changing. We live in an incredibly interesting time where we're changing the notion of the way we do science.
I think this is really a good place to end because we've reached the end of our hour. So we'll stay for any further questions you may have.
Do we have the answer to our homework?
Certainly. I'll send the solution out to Vanessa and she'll email it out to everybody. Okay. You want just the numbers? Yeah, I don't remember them offhand.
Do them on the board.
I can if you give me the numbers, I can show you how to do it. Otherwise, maybe we can talk after the...
Let's talk now after the lecture in case people need to go. Thank you.